Nowadays, in the Volkswagen Auto Europa car factory, the assembly of car components in the production line are mostly made manually by workers. However, when it is necessary to refill any of these components on the assembly line, they are often transported by robots from their storage location to the workers. The Agile project will integrate autonomous mobile robots. These are able to communicate with each other, navigate freely and adapt to dynamic scenarios. This dissertation presents an efficient formulation for the motion planning in multi-robot systems that handles static and dynamic obstacles in the environment. Let's check how the proposed approach generates each vehicle's trajectory for a decentralized system. Firstly, an initial guess trajectory is computed using the kinodynamic rapidly exploring random tree algorithm. Then, this trajectory will be used as an initial guess to an optimization problem that will minimize a cost function until an optimized solution is reached. When formulating an obstacle avoidance constraint in the proposed optimization problem, a set of signed distance fields are used to represent vehicles in the environment through time, thus obtaining non-colliding trajectories for even a 50-robot planning problem. It is possible to verify that all vehicles swerve to avoid collisions with static obstacles and other robots. Additionally, let's check some interesting behaviors that automatically arise from the proposed method. Let's assume that the maximum speed of Robot 1 is lower than the maximum speed of Robot 2. If two vehicles can fit side by side in the same corridor, Robot 2 is able to pass Robot 1. Also, it was tested what would happen if there was only space for one vehicle to circulate. Vehicle 2, even with a higher maximum allowed speed, managed to follow and match Vehicle's 1 speed. The proposed method is very versatile, since it is possible to satisfy several different required performances. In particular, was ensured a road-like circulation, using once again a set of signed distance fields. Here the robots can both drive on their right-hand side. Experimental tests were conducted in a real environment at InesSilva's installations. The vehicle used is a differential drive robot. The trajectories in a real environment are generated successfully. Additionally, the vehicle moves on its right-hand side. Now, we have two vehicles moving in the environment and they swerve to avoid collisions. Since the red arrows represent the vehicle's orientations, it is possible to verify that the generated trajectories ensure that each vehicle drives on their right-hand side. To conclude, the proposed method presented a satisfactory solution to generate feasible trajectories for the preliminary tests in a real scenario.